Assalamualaikum. Good day to everyone. Alright, now we're going to continue our chapter 6 in computational mathematics, which is nonlinear equations. Alright, we will have three types of methods. Alright, the first one is this one, bisection method, and then we will have second method, and the last one we will have Newton method. Before we go to the methods, we need to know what is the problem that we want to solve using numerical methods. Alright, actually we want to find the root of the equation, alright, which fx equals to 0. We want to find the roots if fx equals to 0, when fx equals to 0. So if you can see here, this is the root that you want to find. This is the problem that you want to solve in this chapter, where we want to find the roots where fx is 0. Remember, this is 0, alright, so the equation should be x0 here, the numbering here, coordinate for the roots. So the fx is 0, then we want to find the root of the equation. This is the example where we have the equation here and we find the roots for the functions. This is the normal way where you learn in school, where you will solve it. We solve the function and find the roots like this 0.5 and -3 directly. You will find that this function will become 0 when the x is equals to 0.5 and -3. But in real life problems, we will have much more complex problem that cannot be solved using this type of methods. Okay, so that's why we need to use numerical methods. In numerical methods, we can only estimate the correct answer instead of like this, where we have direct -3 and 0.5 will make fx equal to 0. But for complex real-world problem, we need to use numerical method where we can only estimate, alright, the real number compared to the direct method here. In real-life problem, usually they will not give you an initial value like in class. What we're gonna learn after this, usually in every question we will have initial value, but in real life probably you will not have initial value, so you will need to use graphical methods to plot your equation. Okay, so it's a simple method for obtaining an estimate of the root of equation. So we want to find the root of equation where fx equal to 0, and you can plot the function and observe where it crosses the x-axis. This point, which represent x value, which fx equal to 0, provide a rough approximation. Alright, you will have something here 0 based from the graphical methods, based from the plot that you make. They give you one example here for graphical methods. They give you the fx, right, and then they give you the table. So we need to plot this table, and then we can find the approximation of our x, the roots. As you can see, the graphical methods here provide you the approximation on where to find your roots. When you plot the graph of this function, then we can see the approximation of the roots, okay, where it is not a direct answer. This is not a direct answer for the root here, but we can know where approximately the root will be. Okay, we can see that the root here is somewhere between 1 and 2, but we do not know directly where it is, but from this we know it is somewhere here. As I mentioned before, this method usually used when we have a complex function, where you need to solve complex functions. So here we can make this complex function into a more simple function. We separate this complex function to two more simple functions. Alright, let's say this is a complex function here that we have, although it is not very complex. Okay, so as I mentioned, we need to change it to two more simple functions. So x minus equal to 0, and then we bring this one over here. So we will have x equals to cos x. So this one will be our f1x, and this one will be our f2x, same like what we did here. The next step is we plot these two into the graphical methods here. Alright, we plot them into our graphical methods. When we plot both functions, the intersection between these two, which is located here, will be the roots that we want to find. Alright, for this example. Then we need to find what is the x value for these coordinates. So the x value for this coordinate is here. So it is between 0 and pi over 2. Okay, so we can say that approximation of the roots is between 0 and pi over 2. Previous slide that we have just learned is just a basic of chapter 6, where you need to understand what is the problem that this numerical method will solve. Now onwards, in this chapter we will have one theorem, is what we call as intermediate value theorem. This theorem says that if f is real and continuous in the interval from a to b, let's say we have interval a, b, right, and function a and function b is less than 0, then there is at least one real root. So there can be many roots between this a and b. Okay, so this is what this theorem means. Alright, let's say we don't have graphical that we can see, graphic that we can see. We can plot. Let's see, we can plot. Alright, so let's say like this, maybe. Alright, and then this is A and this is B. Okay, this is your FA. Alright, this is your FB. This is B, and this is the root, right? This is A. Okay, this is the root. Alright, if you see, if we have FA, this one is positive, right? FA is positive, and then we have FB here, which is negative, FB, which is negative, and will be less than 0. So plus minus, this one is negative, right? So we have negative. So does we have a root? Yes, we have a root here. Okay, this is what is meant by positive and negative. Each, let's say FA positive or FB negative or FB positive, FA negative, doesn't matter. Alright, as long as one of them is positive negative and it is less than 0, we can say that they will have a one real root between A and B, between A and B, here, between this and this, we will have one root. Okay, this is what this theorem wants to tell us. If we have plus and minus between them, we will have one or more roots that we will have between A and B. Let's say we have the graphics, right, like this one. So we can say this is A and this is our B, right, between 1 and 2. This is our A and this is our B, right? Alright, so we can prove it by, let's say, FA is equals to F1, right, because we have 1 here. This is our A, equals to, then this equation, 1 squared plus 3(1) minus 5. Then you will have what you -1. What about our FB? F2 equals to 2 squared plus 3(2) minus 5. We will have 5, right? So if we have FA, FB less than 0 based from this equation, this theorem here, we know that FA is -1, FB is 5. So -5 less than 0. So is this true, right? So if you can see, this is our B, this is our A. So it is true that we have one root between 1 and 2. Right? This is what it means. This is what proof that intermediate value theorem, where if you have plus and minus between FA and FB, right, these two value, the start and the end here, if we have plus and minus and it is negative less than 0, we will have one or more root between the A and the B. Okay, this is very important, and you must find, let's say, if you want to solve after this the question, we will see the example. You need to find this first, whether it have a root or not. If it doesn't have a root, if you do the intermediate value theorem, if the questions doesn't have, or the FA and FB is not less than 0, then we can say that it does not have a roots between them. Okay, we must prove this first. We will see in the next example. Again, this is the example that we have mentioned before, where we have plus and minus. Alright, this is plus and minus for FA and FB. This is minus and plus. Alright, this will prove the intermediate value theorem, where we will have one root if we have plus and minus. Let's say we have both let's say here, right? Okay, let's say we will have, this is our FA, this is our FB. So this is FA, this is FB. So both are positive, right? Both are positive here. So if you see this FA, FB less than 0, we know that both are positive, so it will be positive. It is more than 0. So we can see there is no roots, right? There is no roots in this interval, FA and B here. There is no root between here, right? There is no root. So that's what makes it difference between this one and this one, where we have plus and minus, so we will know that we will have one or more roots between the A and the B, compared to if you have both positive, or vice versa, if you change it to both negative, also same. It will be here, there will be no root that we can find if both are negative, right? Okay. Alright, now we come to the method. As we see in our earlier slide, this is about the bisection method, right? Bisection method is under what we call as a bracketing method. The other two, Newton and second, is under open. Alright, this is under bracketing method, bisection. So the forced position method will not be covered in the class. It's not in the syllabus. Alright, so we will have only one bisection method that is from the bracketing methods here. Why we call it bracketing? Because as we already learned before, we will have this, let's say, right? So this is your A and this is your B, right? This is your A, this is your B. Okay, so the root is here. So the bracketing is we bracket the answer, the finding will be the bracket between A and B, between this. That's why we call a bracket. If we want to use the bracketing methods, the most important thing is to make sure that we have a root between the inside the bracketing, inside the bracket between A and B here. We must make sure that we have a root. How to make sure that we have a root? This is where you must use the intermediate value theorem to find the root, whether the brackets, alright, between A and B here, whether we have a root between the brackets. This is very important. If you don't find, if in the bracket A and B here there is no root, you will not find an answer. Okay, so this is why it is, if you want to use the bracketing method, the bisection method here, you must know whether there is a root between the bracket A and B. You must have. If you don't have a root, you will not find the answer. So you must use the previous theorem, intermediate value theorem, at the start. If the question give you the A and the B here, they give you the A and the B, check first. Check for roots. Use the IVT, intermediate value theorem, given to you before. Okay, check first. The question give you the interval A and B. If you want to use bisection, check whether there is a root inside between the A and B. If there is no root, you can say that you cannot use the bisection method. You will not find the answer if there is no roots. Alright, that's the most important thing. You must understand that. Alright, so the bracketing method depends on finding the interval A, B, so that if A, F, B have opposite signs. Okay, we know that we need to check, right? I already mentioned before. We must have two initial guesses, the A and the B. We must have these two, okay, to use this method. And these guesses must bracket or be on either side of the root. So these two guesses, A and B, must be on the other side of the root. Root must be in the middle. So that's why it is important to check for root. No roots, you cannot use this bisection. Okay, this is for usually in your question, in your exam, they will give you the A and the B, right? But in real life, let's say you want to solve a real life problems, you will have, let's say two here, two root here, right? So if you want to use bisection, you need to, let's say, plot first the graph. You need to plot and then find the A and the B, and find the A and the B again for another roots. Let's say you have in real life, you can have 2, 3, 5 more roots. Okay, so for this bisection method, you must use it for each of the root. This one A and B for this root, this one A and B for this root. You cannot use just one bisection method for both of the roots. You must find the A and B for each of the root if you want to use bisection method in real world. Okay, but usually in the question, in your exam or in your assignments, you will have your, we will give you the A and B, and then you can check for the root if you have it or not. Okay. How to start using bisection method? Okay, we already have our A and B, right? Based from our first interval. So this is our A, this is our B. Alright, so we need to use this equation to find our P1. If you notice that this equation will get you directly in the middle, alright, of A and B. So that is where your P1 will be. So this is where you get your half, alright, A plus B divided by 2. So we get your P1 value, which is here. This is your P1. Alright, so you have two new intervals. Before this, you only have A and B. Now we have two new intervals, A, P1, P1, B. Now next, which one we need to choose, whether this interval or this interval, to find our roots. Remember, we don't have a graphical interface. Let's say the root is here, right? So let's say the root is here. We don't know yet, but let's say the root is there. So how can we choose which one of the interval to proceed with our calculations? We use our IVT, the intermediate value theorem back, where let's say for this one, FA FP1 less than 0. Let's say it is less than 0. Okay, when you do this, it is less than 0, so you will have your new interval that you want to check. It is A and P1. The P1 will be the new interval. It is a new B. So we can say that if you're using the IVT, you find out that FA FP1 is less than 0. So you can say that this is your new B1. We don't use this anymore. We will use this as your B1, the new B, for your next iteration. Okay, this is your iteration 0, where this is your A, this is your B. After you get your P1, which one do we want to choose? So you use this equation, IVT, you test both. Let's say for this example, if you do the FA FP1, it is less than 0. Okay, this one FB1, FP1 FB, this one FP1 FB is more than 0. Okay, so we choose this one, which is less than 0, as our next iteration. So the P1 will be your new B1 for your next iteration. That is your first possibility, which is this one, where the value FA FP1 is less than 0, so the root is here. For the next iteration, you will use A P1, so you change the P1 to the new B1. Let's say if the root is here, so you will get this one P1 FA not FA, your FP1 FB less than 0, so you will use P1 B as your next iteration. Okay, and then the P1 here will be your new A1. So this one we go here as your A equals to P1, not B1 anymore, if it is here. So we get less than 0. Okay, so this is the second possibility. The third possibility is when you do this equation, when you divide it, you will get FP1 equal to 0, which is this is the root. So if you get this is the root, P1 equal to 0, then you already find the answer. You are very lucky. So you will find this is your answer. So no need to do the next iteration like this one and this one. No need to do the next iteration because you already found your roots. Alright, so there are three possibilities when you do the division here. When you find your P1, either it is on the left, it is on the right, or you already found the root which is directly in the middle. Alright, this is the first possibility that we have just discussed before, where we can see here if the FA FP1 is negative, which is less than 0 here, the B will be the new the P1 here will be the new B, which is the B1 for the next iteration. And now as you can see, for every iteration, the first one will be bigger than before, and then the next one should be half than the previous one, and then the next iteration should be smaller than the previous one, smaller, until we find the roots. So this is what bisection means. So we divide by half, we divide by half, we divide by half, until we get the root. So this for the first one, this is your new A and B for the next iteration, where you will find another P, say P2 here, and then which one, either this one and this one, and then we will find the next iteration which is smaller based from, let's say, from this one. Again, the next one even smaller. Okay. Alright, this is the second possibility where FP1, FB is less than 0. So this one is negative. So we have our A, then will be our new P1. So this is our A1 for the next iteration. And then we will have this as our A and B for your next iteration. And then this is the last possibility, the third one, where you get 0 for your P1. So this is where you're lucky, where you find directly your roots. So there's no need to go for the next iteration. So this will be your answer. So you can terminate. The root is equal to your P1, so you can terminate the computation. No need to find another interval. Alright, to find the answer, you need to reapply the process to the new interval again and again until you find the answer. Or you can use a termination criteria, alright, based on error. So every question will have an error for themselves. Let's say the error for one of the question is 0.005. So you can use this error as a termination criteria. When you use numerical methods, there should be an error to stop the calculation. So let's say here we have the example here, either one is enough. Either one. Doesn't mean all, either one. If this one is okay, the number one is okay, satisfy the error there, and then you can stop. Even though the second and the third one still does not satisfy the error. Alright, so either one of these three is enough if you can find whether it is less than the error that you have generated. First, you can find out the interval size between the B and the A here, whether it is less than error. If it is less, then you can stop the calculation. Okay. The second one is the P itself. Let's say we have our, before this P1, right? And then we have our P2. So, and we have your P3, let's say. So, if you look back here, P2 minus P1, if it is not equal, it is less than error, you can stop already. If it is less than our error, let's say, which is 0.05, if it's less than that, you can stop the calculation. Okay, before this, the interval, now the P value. The P now and the P previously. If you minus them and it is less than the error, you can stop the calculation. The third one is the fx of the Pn here. Let's say your fx here will be equals to 0.002. If you see it is less than our error. So ideally we want 0, right? But we know that for numerical method it's hard to get 0. So for this accuracy error 0.005, we can say that 0.002 already satisfy our error. So we can accept this as our answer. Okay, remember this is OR here between these three. So either one is satisfied, then you can stop, right? So it's better if you done one of the interval or two of the interval, just calculate these three, okay, to find whether you can stop or not. If you already satisfy one, although the other two is not satisfied yet, you can stop, okay? Because the more calculation you make, the more mistake you can have. All right, you know if you make one mistake earlier, then all the rest after the calculation that you make mistake will also have a mistake in there. All right, make sure that if possible check for the termination criteria early so that you can stop earlier. If not, you will make some mistake in your next calculation. In addition to the previous criteria, we can also use the numerator criteria for determining the number of iteration, which is here n. We can use the formula below, right? This formula. This criteria can also be used to stop the equation that have no solution. If the equation have no solution, you can use this criteria to stop your calculation. In this class, we will only use manual calculation to calculate the interval for our bisection. But let's say if you want to make a program, alright, you can use this algorithm to be applied to your program to calculate the bisection methods. Continuation of the algorithm. Right, this is until the last step of the algorithm. Alright, for bisection methods, this method always converges to a solution, right? Because we already determined previously at the start that FA, FB, right? Remember, must be less than 0. So we must determine this to be negative, right? Then we can only use this bisection method. So it will always converge to a solution. There must be a solution. Okay. The drawbacks, it is slow to converge, right? Means that you need to find this one, the P1, and then you need to do it again, another iteration, and then another iterations until you find the answer. Usually you need to do it like this, so it takes time. But rarely you can, let's say for the third, if you remember, we have three possibilities, right? Rarely that you can get this one, P1 is equal to 0, where this is the root. If you find it directly, this is the answer, so you no need to do the iteration anymore. So rarely you can find this case where you can find the answers very fast. Usually we need to do the iteration. Okay, that's why it is slow to converge. Now we come to the example part. The question asks us to use the bisection method to find a solution with accuracy 2 decimal points for x minus cosine x equal to 0 on 0 pi over 2. The first question that we need to know is, what is the problem we need to solve using numerical methods? Right, we need to find our fx equals to 0. So what is our fx here? This is our fx, right? Fx here equals to 0. So you need to find the function equals to 0. We need to solve this problem. Okay. Let's say if the question give you x equals to cosine x. So how to find the fx? We need to convert into this type, equal to 0. So x minus cosine x equals to 0. So this will be your fx. Why we need to determine our fx here? Because if you remember, if we want to know whether the root using IVT here, if you remember the theorem, right? If we want to know whether the root is between the a and b, so we need to use this equation, less than 0. So we must know our fx in order to calculate this. Alright. Next one is a and b. Do they give us a and b? Yes, they give us a and b. Here this is a, this is b. Okay. Why this is important? If you remember our p1, how to calculate p1 is a plus b divided by 2. So we must have this value in the beginning. Alright. So these three most important things. First, we need to understand what we want to solve. We want to solve the fx equal to 0. Okay, and then we must find our fx. Why? Because of this. And then we must find our a and b. Why? Because of this. Then we need to see the accuracy here. They say is 2 decimal points. Alright. The accuracy 2 decimal points. If you go back to our chapter 5, you know, the error, chapter in error. So 2 decimal point means that 0.0005. If 4 decimal points, 0.0005. Okay. Go back to the previous chapter and then see how we calculate the 2 decimal points. Alright. So do the calculation in 2 decimal points. So let's say if you want to do a calculation for this question, you must use 3 decimal points because our error is 0.005. Alright. Okay, so for all the calculation, we need to use 3 decimal points for this question. Okay, in order for us to find the correct accuracy, easily find the accuracy in the question. Okay, we come to the important part here is to find the intermediate value theorem. We want to find whether we have or not roots between a and b. So we already find our fx, we have our a, we have our b. Remember, because we have 3 decimal points, right? We want to calculate 3 decimal points. So we use 571 here. Pi over 2, 1.571, 3 decimal points. Find our fa by putting our a into the function here. And then you find our fb. If you notice here, it is important for us to find that this one fa is negative. We must take note of this because we will use this throughout the solution. Okay, I will show you, I think, the table that we need to do. Okay, I want you to do the table. So for fb here is positive. Alright, let's say you have your this one is a, this one your b. Your a is -1, which is negative, and this is positive. So you have your p1, right? You calculate p1 after this. So let's say your p1 is positive. So we must have, remember, this ab must be negative. So we will choose this because it's negative positive. Then it will be negative, the intermediate value theorem. Alright, so that's why then the p1 will be the new b1 for your second iteration. We will discuss this later in the next slides, but I just want to inform you. Okay, take note of the sign. It does not always a negative, b positive. It depends on the question. Okay, calculate first the function a and b, and then you see whether it's negative or positive. Alright, because of this one is negative and positive, so this is negative, this is positive, so we get the we will satisfy the intermediate value theorem because we will have the negative less than 0. Okay, so we have a root between 0 and pi over 2. You must do this first. Remember, you must do this first in each of the questions before you continue finding the roots. You must make sure that you have a root between the a and b first. After finishing finding the compulsory thing where we need to find the roots, whether we have a root or not between our a and b, which we have done in the previous slides, now we can continue by finding the p1 here. Right, we already know our a and b, which is 0 and 1.571. So we will get our P1, which is 0.786. So to illustrate, so this is your 0, A and B, 1.571, and this is your P1, 1.786. So which one do we need to choose to continue our interval, the next interval? So we need to use our IVT, the theorem, right? Whether it is less than 0 or not. So if you can see the FP1 here, you get your answer is 0.079. It is positive. Your F0 is negative. So we need to have one negative and one positive, right? One positive in order for us to choose the interval here. So we know that this is negative, this is positive. So these two, F0 and F0.786, is less than 0. We know that F1.71 is positive based from the previous slide. So this is negative. So this one and this one. So we choose this interval 0 and 0.786 as our new interval for the next iteration. Okay, this is the table that I mentioned to you before. If you remember, I asked you to take note, right? What is our sign for our A and B? If you remember, our FA here is 0, B is pi over 2. Our FA, the sign is negative, right? For A and positive for B. Then if you calculate your P1 here, the first P, it is positive. The sign is positive. So we should replace the P1 here to the B position. So this is your B1 for your second iteration, right? Because remember, FA, FB less than 0. So this is minus plus, right? So when you got the second iteration, this is minus. So which one of the plus you must use? You must take this plus here to replace the plus before. So 0 pi over 2, and then the second iteration will be 0.786. It will become smaller, and then you find your P2, and then it become much more smaller, and then we'll see which way it goes. Then if you calculate your P2, A plus B is 0. This is your new, right? Your B1 here, 0.786. So you will get your 0.393 as your P2. So if you calculate the function for P2, you will get negative here. So we know that this one 0 is negative, this one is positive. So this one is negative. So we take the interval between these two, right? So 0.393 and 0.786 as our new interval. Remember now, okay, this one is negative, right? So the previous A here is negative, this one is positive. So we must have positive and negative to be less than 0. So this will be the new A. Okay, this is the second interval here, 0.786, right? So when you get your P2, it is here, but this is negative, this is negative, this is positive, right? So we take this interval, not this. So the A here will become the new A1 here. Alright, it will change that. Don't make mistake on this. So this is minus and plus. Say all minus and plus, minus and plus, minus and plus. So this one will replace the previous A. So we take this one, and then we find another iteration if we need to. Okay. Right, this is the example of a table. If you do until the fifth iteration here, like this question, right? You do until fifth iteration. So I think it's better if you write, when you do the table, just write another FA here and FB. Okay. to make it proper, so we can see how many iterations, what is the A, what is the B, and the FA and the FB, along with the P, P1, P2, P3, and the F for the P. Then we can see the sign, whether it is negative or positive. We can see directly from the F here. Okay. So how to stop? Remember, we have our error is 0.005, and we have three type of things that we need to check. The interval, remember we have three things. The interval, we have interval, the Pn minus Pn minus 1, and then the Fp, right? One of the value here, interval P and the function of Fp must be less than 0.005. If we find one of these, either one of it less than 0.005, we can stop and we can stop the calculation and take it as the answer. So you can directly check the interval b minus a here. Alright, we can check b minus a directly from the table. See whether if you minus them, it is less than error, or between this p here, the p2 minus p1, p3 minus p2, can check whether it is less than 0.005, and you can check the function of p here directly whether it is less than 0.005. So for this question, we can see at iteration number 5, the function of p here is 0.003, which is less than 0.005. Before this, there is none, right? All is bigger than 0.05. And if you calculate minus the p interval minus the b minus a, the interval also, it is more than 0.005. So this here satisfies the third one here. So you can stop calculate until this iteration number 5. So you can say that f, the function of 0.737 is equal to 0.003, which is less than our error. So we can say that our P5 here is 0.74. This is the answer, where, remember, 2 decimal points, so we need to 7, so 3, 7 become 4. 0.74, 2 decimal points as the answer for this question. The next example, same thing. You need to find your fx, you need to find your ab. Okay, this is your ab, this is your fx, right? And then you need to know your accuracy, and then do the calculation, the decimal point based on your accuracy. Alright, this is 0.005, so 3 decimal points. Alright, so again, find your fx, you know your a, you know your b, and then you know your error here. So you need to first do the IVT, you need to do the theorem first to know whether you have or not the roots between a and b. So you insert your a and FB here, so you get your A is positive, your B is negative. Remember, you need to take note on this, and then you need to provide the table. So because of this one is positive, negative, so it satisfies the equation. So we have a root, then you can do the calculation to find the root between the A and the B here. And find P1, we have our A and B, right? 0 and 1. So you find your P1, and then after you find your P1, function of P1 here, you will get it is positive. So back to the previous one, which one is positive and negative? So we have this one is positive, this one is negative, the B, right? So we will use our positive negative of 0, the new this is your A1, right? This is the new one, this is your B. So we need to use the new interval for our next iteration. Look at the table. Okay, as I mentioned, you have your, this is your previous A, this is your first B here. Then your first P, you got 0.5, which is positive. So which one you need to change? You need to change here, right? Because this is positive, so this one will change the A, become your A1. Then the B is the same. So you calculate your P2, so you will get 0.75. So you do the function of 0.75, you get negative here. So if it's negative, so we will change your B, right? So you become your B1 and A1 here. We check the table. Okay, you get 0.75. This is your B negative, right? So this one should be under here. Okay, and then this is plus and minus, right? Okay, so if you see the example here, again, for it is better if you provide FA. If you make this table, provide the FA and provide the FB to make it a proper one, alright? Remember, our error is 0.005. This is where you want to stop your calculation. So this is your interval, first, 2, second, third, fourth, fifth, sixth, and seventh interval. Alright, so how to stop? If you get your answer is under the your P here, is under your error 0.005. Okay, so there are three ways. Again, we have three ways. We can see whether B minus A for each of the iteration. After you calculate, you can find it, or between the P, this one, and this one, and this one, each of them, minus between them and see whether it is less than 0.05, or you can see the FP whether it is less than 0.005. Okay, then you can stop. Either one, doesn't matter. Either one satisfy, then you can stop. For this here, we can see generally if the number getting lower, right? The number getting lower, usually you can find the answer. Okay, and the answer is based from the value of P here, right? So based from these three interval, P value and the FP, for the 7 interval here, we find that 0.04 here is less than our 0.005. So we can stop here. Okay, we can stop here. So this will be our final solutions. Remember, check everything. Check. Sometimes you can find the answer earlier than usual. Don't just wait for the value of FP. Sometimes you can find the value of interval here or the value of B minus A here is less than 0.005. Okay, so for each iteration, calculate those three. Okay, just for this example, again, this one satisfy first. Okay, for this example, same as previously. Alright, so this is how you do the answer. Alright, so you say F 0.570 is equal to 0.004, which is less than our error. And then P is equal to P7, P iteration of 7, which is 0.57, 2 decimal points. So because of we do numerical methods, we need to provide the whole answer here, 0.57 brackets, how many decimal points. We need to have this. You need to have this as your answer. Okay, 0.57, how many decimal points? For us, 2 decimal points, because this is the approximation, right? This is not direct answer. If we do direct answer, 0.57 is the actual value, but this is not. This is the numerical method, so we have approximation, we have error. Okay, so this is true on 2 decimal points, so we need to reiterate this in your answer. Alright. Okay, we have exercise here for you to do, and I think we can discuss it in our next class.